eigenvalue of the Laplacian change with respect to the domain? Please.
Thank you so much. First of all, I would like to thank the department and also Vladimir Bobko for inviting me, and also this Basis Foundation Travel Club. I'm going to talk about how this eigenvalue of Laplacian changes when we change the domain. And as we know, this the eigenvalues depends on the geometry and the size, shape, and all that sort of things of a domain. So this is a joint works with my PhD advisor, Professor Keshavan, and my PhD student, Ashok. And so these are like a couple of papers to these different people. Another one is my PhD student, Mukund. So mostly I'll be discussing results from three different articles with so let me start with this problem. So when you have eigenvalue of Laplacian, so we want to know which domain either maximize or minimize this eigenvalue. So this started with this famous conjecture of Rayleigh. So he's conjectured that among all vibrating elastic membranes of constant density and fixed area, the circular membrane has the minimum principal frequency. So in the language, mathematical language, so what it says, among all planar domains having equal area, only the disk minimizes the first listed eigenvalue of the Laplacian. So more precisely, if you look at this eigenvalue problem, minus Laplacian u equal to lambda u in omega, and u equal to 0 on the boundary of omega. So you look at a domain omega, and then one can look at the first eigenvalue using this variational method. So one can obtain lambda 1 of omega as the infimum of L2 norm of gradient u square, gradient u for u in h10 of omega with L2 norm of u square. So if we minimize this energy over this unit ball in h10 of omega, L2 unit ball in h10 of omega, we get lambda 1 of. And similarly, we can look at omega star, which is a ball in R2 with the same measure as omega. So look at the same this quantity instead of omega on omega star. Okay. So how this lambda 1 of omega and lambda 1 of omega star are ordered? So it's a question. So Rayleigh conjectured that the lambda 1 of omega star is smaller than lambda 1 of omega. So he posed this problem around 1980s. Then so the proof of this conjecture was so this was question planar domain. So it was proved by Faber for planar case, and Kran also independently proved this result for planar case, and then Kran extended this result even in a higher dimension and bigger than equal to 3. He proved this inequality. And nowadays in literature, this inequality is known as Faber-Kran inequality, or some people call it as Rayleigh-Faber-Kran. So this proof, the proof uses this Fourier formula and isothermal inequality. So one can give a simple proof for this result using this short symmetrization. So let omega star be the ball in R2 centered at the origin with the same measure as omega. So now if you given a function on omega, real valued function on omega, so one can find a function u star, so which is called short symmetrization of u, which has the property that if you look at the level set of u star, so this is a function on this ball. Okay? So this level set is same as the star of level set of u. Okay, so this is a ball. So this is a ball of same measure as the level set of u bigger than or equal to 0.
Что означает звездочка справа? Спросите по-английски.
Симметризация пошла. Звездочка означает это шар.
Верхняя звездочка это шар.
Да.
Наверху написано omega.
You mean star?
So star, yes, just explain in Russian. So star means that is the ball.
Yeah, it's a ball. It's a ball centered at R2 with the center origin. Okay, so before I said omega star, which is can be any ball. So here I'm just fixing the ball with the center origin. Okay. So what it says, this u star is kind of a radial function which is radially decreasing.
No.
And so its level sets are basically both. Okay, the level sets of U star is basically both. And what is important, the LP norm of U star is same as LP norm of U. And if you look at the energy, the gradient norm of this U star, so that is smaller than or equal to LP norm of gradient. Okay, so this inequality is called as Fourier-Segal inequality. So the short symmetrization also this decreases the gradient. So now the proof can be given in a symbol in 2 lines.
Yeah.
He uses arbitrary function, right? For Schwarz symmetrization, it is defined for arbitrary function.
Arbitrary function. Yeah.
But then it is
Yeah. So
applied
when
for
you need the gradient, you will look at H1 or yeah. Right. Yeah. So now if you take the first eigenfunction of Laplacian on omega, so and we can choose this eigenfunction so that this phi1 is bigger than 0. So this is just a maximum principle, and L2 norm is equal to 1. So we just normalize it that way. So then so we look at the short symmetrization of phi1. So since phi1 is a non-negative function, so this its minimum will be on boundary. So it will be a valid test function in H10 of omega star. And it has so since the symmetrization preserves the LP norms, so the L2 norm of phi1 star will be 1. So now let's look at the variational characterization of lambda 1. Lambda 1 of omega star is less than or equal to infimum of, okay, so the star is here, so and the gradient U and U from H10 of omega star with L2 norm of U star. Okay. So now what we seen is this phi1 is a varied candidate in this equation. So therefore, this infimum will be smaller than or equal to L2 norm of gradient phi1 star. And by Fourier-Segal, we know this is less than or equal to gradient phi1, L2 norm of gradient phi1, and that is precisely equal to lambda 1 of omega because phi1 is a first eigen. So this basically proves this Rayleigh's conjecture using this Fourier-Segal inequality. So now, so one can ask the question: so what if you instead of Dirichlet boundary condition, so you assume the Neumann boundary condition? The dou u by dou eta equals 0 on the boundary. So in this case, if you look at the first eigenvalue, that will be 0 because the constant function basically satisfies this equation. Okay. So you look at the first non-trivial eigenvalue of this Laplacian with this Neumann boundary. So that has this variational characterization. You minimize this gradient U square in H1 of omega, and L2 norm of U is 1, and the additional condition that U is integral U is 0. So which basically says that these functions are orthogonal to the first eigenfunction, which are constants. So then one can ask, so this question, what is the relation between mu1 of omega and mu1 of omega star? So then Kornhauser and Starkwold in 55, they conjectured that among all planar domains having equal area, the disk maximizes the first Neumann eigenvalue of the Laplacian. Okay. So in the Dirichlet case, it was Wald was minimizing the Dirichlet eigenvalue, whereas Neumann eigenvalue, the disk maximizes the Neumann. Okay. So this conjecture was proved by Segal in 1950 for the planar case. So he assumed some more regularity on omega. Then Weinberger extended this result for higher dimension without any restriction on the domain. And so in literature, this inequality is known as Segal-Weinberg inequality. The first eigenvalue, Neumann eigenvalue, is maximized by. So now let's look at the problem where the ball is not no longer a candidate for the extremal domain. Okay. So we want to look at a problem where we have a doubly connected domain. It has two boundaries, okay, at least two boundaries, and we keep the boundary condition like so the Dirichlet boundary on outside, and inside we keep Neumann boundary condition. So one can look at the eigenvalue, this eigenvalue problem. And here we assume something like omega d is a domain without any hole, and omega eta can be like a union of finite number of domains without holes. So it's like we can assume you can have multiple holes inside, and omega is a domain of the form omega theta minus omega eta comma. And we assume this domain is Lipschitz so that we can have this Neumann boundary. So the first question is, so what is the extremal domain for such eigenvalue form? So here we are looking at a class of domains which has a hole. Okay, so the ball is not a candidate in this case, in this class. Okay, so naturally, one can expect the annular region is the candidate. Okay. So then, so there are many choices of annular region. Okay, so if we fix annular region with the same measure as omega, we can have many annular region with the same measures. Okay, so then what is the right annular region which extremates this eigenvalue? So we choose this annular region omega hash, which is a ball minus a BR, B capital R minus B small r quotient, which has the property that it's the outer perimeter, okay, is same as the outer perimeter of the gamma D, and the same measure. So in a way, we choose this capital R in such a way that the boundary of outer perimeter of this VR is same as the outer perimeter of gamma D, and small r we choose in such a way that this measures are same. Okay. So in this way, we can fix a unique annular region. Okay. So now the question is, so we can consider this eigenvalue problem, mixed eigenvalue problem in this domain, and mixed eigenvalue problem in this domain. Okay. So what is the relation between the eigenvalues? And so I said if we have multiple holes inside, okay, so this outer perimeter won't change because it is the same perimeter as gamma D, okay, but the inner R will change so that this will have same volume. Okay, so now even if we consider a domain without a hole, okay, so in this case also this ball will have so the perimeter, outer perimeter of this ball is same as outer perimeter of this. Okay. So we need to choose this smaller so that this volume is same. Okay. So as we know, this ball has the least perimeter with having the same volume as this. Okay. So there will be a hole. Okay. So even if you assume the initial domain has no hole, okay. So this can have a hole. So now we looked at this mixed boundary value problem with this outer Dirichlet and inner Neumann boundary. So as before, we can give the variational characterization for this first eigenvalue. So the constant function is not a valid choice because we are assuming u equal to 0. So we don't need that orthogonality condition. So we are varying this over h1 of omega with the condition that u equal to 0 on gamma d and L2 norm of u equal to. So we can look at tau 1 of omega and tau 1 of omega hash. So the question is how these quantities are related. So we know, like in the case of Dirichlet, ball minimizes and the Neumann ball maximizes. Okay. So here we have a mixed one, both Neumann and Dirichlet. So now what? So indeed, so this reverse of Poisson inequality code happens here, holds here. So we call this as reverse Poisson. So this result was proved for planar case by Payne Weinberger, and Hirsch gave a different proof for this result in 63. And if there is no hole, okay, so which means this is like a first eigenvalue. Okay, so this basically you see a first upper bound for the first eigenvalue in terms of this the mixed eigenvalue. Okay. So we have one more constraint. We are both the constraints are both on volume and the outer perimeter. Okay, so we know that if we don't have any restriction on the outer perimeter, this lambda 1 of omega can go to infinity. Okay, so there is no upper bound for lambda 1 of omega. But if we keep a constraint on the perimeter and the volume, then this lambda 1 of omega can be bounded above from this mixed eigenvalue. And we extended this result for higher dimension. under the restriction that this outer domain is above. And this this extended this. Okay, so this again 2020 for convex. Okay, so that means this result always is a simple consequence of this fact. And we again give another proof for this result and also prove the uniqueness of this domain when omega d is convex. So I will give you an outline of how one can prove this result. The main ingredient of this proof is what is known as Nagi's inequality. So this symmetrization techniques what we used for the case when there was no hole won't work in the case when we do with consider this problem with on domains with holes. So we for a domain of let's say A is a set. So let's look at this inner parallel sets. So which basically the set of points which is delta distance from the boundary of. Okay. So we get a line like this. So we call it as an inner parallel set. And one can also look at the corresponding. So this. Okay. So let me. So the Nagy, what he said. So if you look at this measure of this set, okay, so this is always less than or equal to the perimeter of this this outer boundary minus 2 pi delta. So this called Nagi's inequality. I will show you like how it is related with the perimeter. So now what we can do, like let's look at this measure of L delta and measure of L delta hash. So L delta hash is precisely like you look at the ball with the same measure as A. So then, so from the this ball, so from the outer boundary, you look at the line which is a delta distance from the the boundary of the ball. Okay, so from the circle, from the outer circle. So here we get this this inner parallel sets are basically the circles here. Okay. So here we get some arbitrary shape curve. So now what Nagi's inequality tells that so you look at this the measure of perimeter of this L delta, so that is less than or equal to perimeter of the L delta hash. So let me call this S delta as the perimeter of L delta, and V delta is the integral of this S of t dt. So this basically the volume of this parallel body. Okay. And then look at the same quantity for this angular region. Okay. So then what one can observe that this so Nagi's inequality basically tells us that S delta is less than or equal to capital Z.
Excuse me.
Yeah.
This is two-dimensional case.
This is two-dimensional. Yeah, two-dimensional. So this Nagi's inequality is two-dimensional. That's this 2 pi delta is coming because of the two-dimension, right? So then, so this also tells you that the volume also has this same ordering, and then we can also show that so some quantity like this also has this order. Okay. So we will see why we are interested in this function. Okay, so yeah. So now the idea is like so we have if you consider the eigenfunction on this angular region, we know that this is a radial eigenfunction. Okay, so we want to lift a radial eigenfunction to another domain which is of this shape. Okay, so how do we do it? So if you take a radial eigenfunction, we can write it as like f of r minus mod x, and this r minus mod x is precisely delta 1 of x. So that's the distance of x from the boundary. Then let's just insert this volume. Okay, so we want to write u star in terms of. Then I'll call this f v inverse as this function phi, and this v is as it is and delta 1. So basically, I want to rewrite this this radial function using this volume bracket. And this is the on omega hash. So what I do in on omega, so I will take this phi from whatever I got it from here, okay, and this volume instead of capital V, I'll replace it with the small v, which is related to this omega, and delta 2 is a distance from x to gamma d. So now what happens? So basically what we are doing here is like, here we know that for a radial function, these are the level set of this function is precisely the circles. Okay. So here we define a function on omega whose level sets are basically the integral parallel sets. Okay. So now what happens so let's see what happens to this gradient energy and this L2. Okay. So the gradient of V, okay, so V is this function, so you will get this phi dash and then V of delta 2 and this derivative of V. So V is defined using the integral of S, so therefore the derivative will be S delta 2 of X. Then we'll have to look at the derivative of delta 2, which is, we can show that is always less than or equal to 1. And therefore this gradient will be, the L2 now gradient will be smaller than or equal to this. So now one can use a Fourier formula to write this this as integral 0 to t star and integrate this over this parallel lines, interior parallel lines. And we know this here, this delta 2 of x is constant. Okay, so we can replace this delta 2x with a t, and this is with it. So now what happens on this? So let's take v of t equal to let's alpha, and then this is phi dash of alpha square, and we know this these functions are constant on this parallel lines, okay. So that will come out, and then s of t will be v inverse of alpha square, and then we'll have it here. So now we can replace this SV inverse of alpha. We know that SV inverse of alpha is smaller than or equal to capital SV inverse of alpha. And we compute this with the SV inverse of alpha. We precisely get the L2 norm of gradient U hash on omega star hash. So therefore, this process basically decreases this L2 of gradient. And so the similar calculation we can show that it preserves the L2 norm of V is same as L2 norm of V hash. So now one can use this this variational characterization. So here the U hash has a larger energy. So therefore, if you start with the eigenfunction on omega hash, so this is a valid candidate for a test function on omega. Okay. So therefore, we get the first eigenvalue of on omega will be smaller than or equal to the first eigenvalue on omega hash. So this basic idea of this interior parallel is how to lift a radial function from this angular region to omega. Okay. So if you see this proof in this proof, I mean, so here I'm not using anything in the dimension 2, except so if I have this result, okay. So all these things holds even in the higher dimension, okay. So only thing, so this is given by this Navier inequality. Okay. So the Navier inequality gives me this, and then all other things follows just like that. Okay. So now the question is, can we get a Navier type inequality on higher dimension? So if that is true, then we get this same result on this on higher dimension. Okay. Yeah. So the question is, can we prove a Navier inequality in higher dimension? So for proving that, let me give you another way of looking at the Navier inequality using the perimeter. Okay. So let's start with a simply connected domain. So so the L delta was this line, which is, has a distance delta distance from the boundary of A. Okay. So now let's look at the set, which is delta distance away from the boundary. Okay. So this is a kind of thick set. And then what we can see, this L delta is basically the boundary of this A delta if it's a simply connected domain. Okay. So if there is a hole, this can have something else. But if it's a simply connected domain, so this boundary of A delta is L delta, and therefore the volume measure of this L delta is precisely the perimeter of A delta. And if you look at the corresponding thing for this A star, which is a ball of the same measure as A, then yeah, maybe yeah, I think so. This A hash, so this is not star A hash, which has the same outer perimeter as A. Okay, so not a star, it's a hash. Okay. So then the perimeter of A delta hash is in the dimension 2, it is 2 pi r minus delta because it's a ball. So this set is basically the ball of radius r minus delta. Therefore, the perimeter is basically 2 pi times r minus delta. Okay. And this is so 2 pi r is the volume of measure of this outer boundary of A. So we can write this perimeter of A delta hash is precisely equal to this quantity. Okay. So now what is Navi's inequality is this one. Okay. So we can rewrite this in terms of this perimeter inequality. Okay. So the perimeter of A delta is smaller than or equal to perimeter of A delta hash. Okay. So this is the ball of radius r minus. So the Navi's inequality is equivalent to this inequality between the perimeter of these two quantities, these two sets, which are this is for simply connected. Okay, just be careful about that. Okay. So now, if we have this, we get this L delta measure of L delta is less than or equal to L delta hash. So all these things, whatever I did for planar case, we'll go through. Okay, if I can show this inequality. Okay, so whether that is true or not. So this is indeed true. Okay, so what we need is two different inequalities. So one is called Alexandrov-Fengel inequality. Okay, so which relates inequality between something called Koermas integrals, which are some geometrical quantities associated to this domain omega. Okay. So for example, if j equal to 0, this W naught of omega is the volume, and W1 of omega is perimeter of omega by. Okay. So for example, in dimension 2, so what we are interested in these two quantities, W0 and W1 of omega. So basically, Navi's inequality basically gives some relation between this. Yeah.
Do you have an explicit formula for this Wj?
So there are formulas using this quadratures and all. So yeah.
For example, I don't know what is queer machine.
Yeah. So let me. So this is for example for a ball. So these quantities are omega n times r power n minus j. Okay. So for other domains, this involves other curvatures. But what we are interested this this kind of isoperimetric inequality, which we don't want for every I and j. So I will show you like what are the quantities we are interested. Yeah. So for example, if j equal to 1 and I equal to 0, so j equal to 1 and I equal to 0, we get this inequality. Okay. And what is W1 of omega is something in terms of perimeter of omega, and W0 in terms of volume. So if you substitute all this quantity and simplify, so what we get this. Okay. And this is precisely the classical isoperimetric inequality. Okay. So this Alexandrov-Fengel inequality is basically the extension of isoperimetric inequality for other Koermas. And for j equal to 2 and I equal to 1, so we get an inequality connecting W2 of omega and the perimeter. Okay. And we are basically interested in this.
Володя, Александров АД имеется в виду, да?
Да.
О, спасибо.
It's about
Alexander is geometer.
Okay.
The famous geometer. Yes?
Yeah.
there are several mathematicians.
Okay. Okay. Yeah. So then the second ingredient is this relation between this this derivative of P of omega, gamma t. So the gamma t is basically the set which is t distance away from the boundary. So so let's look at the r of omega. This is the in radius of omega. So the radius of the largest ball contained in omega. then we have this inequality between the derivative and W2 of omega. So this is not required. Okay. So if so what I want to say, if equality holds, this must be both. So let's recall. So we have from Frenzel inequality, we have a relation between W2 of omega and perimeter this way. And the second ingredient is this this derivative inequality between derivative and derivative. Okay. So now let's take all these things. Okay, so the derivative. So instead of W2 of omega t, so using this Alexandrov-Frenzel inequality, I can replace omega t W2 of omega d t with the perimeter of omega t. So I'll just substitute that here. So now what it basically says, if I look at the derivative of p of omega t power 1 by n minus 1, okay, so this inequality basically tells me that this is bigger than or equal to this quantity. Okay. And now for a ball, there is a equality holds everywhere. Okay, so in Alexandrov-Frenzel and also in this derivative inequality also you have equality. So basically you get this is equal to n omega n power 1 by n minus 1. So if you work with this ball, okay. So now if you I think so I so this is a hash, not star. Okay, so sorry about that. So if you combine both these things, what you get a relation between this the perimeter of omega t and perimeter of omega t hash, not star, it's a hash. So now just integrate this inequality. So what you get is perimeter of omega delta. So if you integrate this from 0 to delta, so you get this inequality between omega delta and omega delta hash. And that is precisely what we need to prove the this Navi's criteria.
So convex, right?
Yeah. So here we assume the convexity of omega, so which basically gives all these things holds. So the Alexandrov-Frenzel inequality for convex domain, and this is also for convex domain. So we need convexity to get this inequality. Yeah. So this is what we need is a convexity for the omega d. Okay, not the convexity. I mean, we are considering a domain with the hole. Okay, so that cannot be convex. What we need is the outer one, omega d is a convex domain. So inner can be anything. The holes can be of any shape. Yeah, so now one can ask the question. So what we considered before was Dirichlet outside and Neumann inside. So one can ask the reverse question. So you keep Dirichlet inside and Neumann outside. Okay. So what happens in this case? So here, so the extremal domain we choose in such a way that the perimeter of this inner perimeter, or perimeter of gamma d, is same as the inner perimeter of this under region. Okay. And we choose this under region. So the capital R is chosen in such a way that the volume of this omega and omega hash is same. Okay. It is different from the omega hash what we consider in the other case. So where we consider this outer perimeter of omega hash and outer perimeter of omegas are same. So here we fix the inner perimeter of this gamma omega and the n-1 the Quermas integral. Okay, so for planar case, this boils down to the perimeter constraint. Okay, but in higher dimension, it is a restriction on the n-1 Quermas integral.
So the previous slide was about a planar case, right? Well,
This
this
one.
one, yes, or it's any.
So this we could do it with the restriction if this is a board, even in the higher dimension with the perimeter constraint. Okay, but not with the for any general convex double with the perimeter constraints open. This problem is open.
Я правильно понимаю, что сама омега это просто шар, да?
Да, да, да. То есть это внутренняя вот эта дырка.
Внутренний.
Это шар. Она еще любая.
So basically, what we are doing, like we are wherever we have the Dirichlet condition, so we choose another region so that this perimeter and this inner perimeter are same. Okay, so if it is the inner Dirichlet condition, so we keep inner perimeter as same. If it is outer Dirichlet, we keep outer perimeter. Okay, so this works if we have like when the omega d is a bond, we could prove it for high dimension, but not for in convex term. So now instead of the perimeter constraint, so we choose this n-1 Quermas integral, so which is basically a perimeter in the case of planar case, but it's a different Quermas integrals in the case of high dimension. So in this case, we could prove that this under region maximize this first eigenvalue. Okay, so we have reverse over that where this is a concentric under region whose inner perimeter is same as the has this not perimeter n-1 mass integral is of gamma omega d is same as the wn-1 mass integral of dn. So this is accepted and going to appear in this PMNA. And so one can ask the question like if you keep two Neumann condition. Okay, so on both boundaries, if you have Neumann condition, so we have some results on this even for the higher eigenvalues. So this is known as Segow-Weinberg inequality, because we have both the sides we have Neumann conditions with some symmetry assumptions on domains. We have inequality for the higher eigenvalues. Okay, so this is a work with the logical both and for some. Yeah, so now one can ask what if we keep Dirichlet on both sides? Okay, so this question is answered in the in planar case with this restriction, and this problem is completely open in a general domain in n bigger than equal to. So, and this condition is very natural. So you are looking for an under region with same measures, and you need some conditions on the inner and outer boundaries. Okay. So this is. So one can have like similar conditions on the high dimension. So instead of 4 pi, you will have something on the volume, but still this one could not answer this inequality in the high dimension. Yeah, in the planar case, what was the key result was something called the effectless cut. So basically, it splits the domain into two. Okay. Like you can have a cut inside where this Neumann boundary condition is satisfied. Okay, so you will have two problems. One is inner Neumann and outer Dirichlet, and inner Dirichlet and outer Neumann. So basically, that allows Hirsch to conclude this result. And similar results for high dimension is open. So we are with Vladimir, we are working on this kind of result. Now we in planar case, but we are trying to do it in a higher dimension. So the next part of my talk, I'll be talking about the monotonicity of the first eigenvalues. So so far we have seen like if you look at like domains with the same volume or something, so which one maximizes? Okay, so we don't know like if you take two sets with the same volume, so how the eigenvalues are related. So that's a very general questions to answer. Okay. But what we can do, like we can look at say two domains of same volume. Like, for example, with like shifted like eccentric under regions. Okay. So let's look at omega s. This is Br minus Br S1 quotient. So And we want to know, like, so let's look at lambda s is the first eigenvalue of lambda 1 on omega s. So we want to know, like, what happens when this s is moving towards this s varying over 0 to r minus r. Okay? So basically, we want to know, like, what happens if this inner bond move towards this outer bond. Okay? So the previous results will just says that the concentric one maximus. Okay, it won't say like what is the relation between like, let's say, like S1 and S2, how the lambda 1 of S1 and lambda 1 of S2 are related. So lambda 1 of S is strictly decreasing. So this was conjectured by Ram and Shivkumar using some numerical calculation, and they gave a proof using some argument of Ashburg and Chetalian in 1999. Then Harel, Fluger, Kureta, they proved this result, and independently Cashman also proved this result for n bigger or equal to.
A question.
Yeah.
Limit lambda for first at 0 is 0 or not? Предел лямбда 1 при стремящемся к нулю 0?
It's a maximum.
Нет?
S это как бы положение внутреннего шара. Да?
Да.
S равное нулю, это значит у вас концентрические шары.
Картинка справа.
Да.
So it's a maximum and then it decreases.
So I see.
Yeah, it decreases too. Yeah. So the idea of the proof is basically this Hadamard perturbation formula, which gives an formula for this how this derivative of this lambda 1 of s. So this function lambda 1 of s is basically differentiable, and it has this formula. So the normal derivative of, so us is the eigenfunction, the first eigenfunction on this domain omega s, and you are integrating this normal derivative on this the inner bond. Okay. So then another ingredient of the proof is this reflection techniques. So you consider this eigenfunction, and also the reflection of this eigenfunction on this part. Okay. So let's say u is the restriction of this eigenfunction on this part, and v is the this reflection of this part on the this region. Okay. So basically, like you consider this, if you reflect this outer boundary inside, so you get a region. Okay. So basically, you reflect that back. That is this. Okay. So the US on this reflection of this with respect to this line. So now the question is, so if you want to get a relation, the sign for this. Okay. So if you can show that this this V has a smaller normal derivative, then basically you get a sign for it. And that one can prove it using one is the comparison principle. So u is 0 on this, and v, because this associated function is non-negative, therefore v restricted to this boundary is strictly positive, and on this side of this domain both v and u are same. Okay. So now one can use the comparison principle to say that v and u has this relation inside this part. Okay. And then one can use a strong maximum principle to say that v is strictly bigger than u, and Hoff-Lemma will give you that the derivative of w is negative, so which will tell you that the normal derivative of v is smaller than normal derivative of u. Okay. So that is so if you look at on this part, okay, so this part will have a smaller normal derivative. Okay. And then this eta one has a different sign. So this side is positive and this side is negative. Okay. So which basically conclude that lambda 1 of s is dash is negative. Okay. So this is the principle that people uses. So, and one can do this for the P-Laplacian. So we have the Hadamard perturbation formula. And what we are missing here is a strong maximum principle. Okay. So we could avoid bypass this strong maximum principle using this this nature of this domain. So basically, we can we prove some radiality near this inner boundary and radiality near outer boundary and which basically gives us a result which is says lambda 1 dash of s is strictly less than 0. So that's what we did in this paper with Vladimir and one can do instead of this Dirichlet, if you keep Neumann derivative outside. Okay. So one can have the same perturbation formula. Okay. So what we are missing here is we know this Neumann derivative is 0 here, okay. And we don't know what happens to the Neumann derivative of V. Okay. So in the previous case, we know this eigenfunction is positive inside, so we could get that V is positive here and U is strictly U is 0 and V is strictly positive, which gives us some comparison. We can compare that. Okay. So here we don't know what is the normal derivative of V on this boundary. Okay. So what is the sign of that? So and we proved we get a sign for this normal derivative using this geometry of first eigenfunction. So where we could show that this eigenfunction has this property. So one is the Fourier short symmetry, which basically says that this eigenfunction on each circle, so this increases along each circle, okay, from this side to this side, and it's symmetric with respect to this. And the other one is affine radiality, which says that if you move from this center to this, so this function is strictly increasing. Okay. And then there is a monotonicity in even direction, which says this along this direction, this eigenfunction is strictly decreasing. Okay. So we proved this geometry. So this was a picture from we proved it got in Mathematica, but analytically we could prove all this result. Okay. So this is the Fourier short symmetry, and this is affine radiality, and this U is strictly decreasing in the even direction. Basically means that the derivative of U with respect to x1 is. And with this, one can show that the normal derivative of V in this outer boundary is basically strictly positive. Okay. So this is the normal derivative. So we can split this into this affine radial and this direction in E1. Okay. And both these quantities are positive. Okay. So that's what we proved in. And then we proved this comparison principle that works with the Neumann boundary conditions, and we could get a result using this this Hadamard perturbation formula. So how much time I have?
10 minutes.
10 minutes. Okay. So then I will give you another way of proving this monotonicity result using a simple polarization. Okay. You don't need this Hadamard perturbation formula, and this is applicable for many perturbations domains which it does not have certain symmetry. So what is a polarization? Polarization is any affine half space in Rn, we call it a polarization. And sigma h is a reflection with respect to the boundary of h. Then for a domain omega, so we define a pH of omega, which is a polarization, called the polarization of omega of this set. Okay. So for example, omega is this set, then pH of omega. So to find pH of omega, we'll reflect this omega, okay, so which will be something of this sort. Okay. And on x side, we take a union of omega and sigma h of omega. And in the complement side, we'll look at the omega and sigma h of omega. Okay. So for example, this ellipse, okay, so we'll transfer to this heart-shaped term. Okay. So then, so the question is, can we compare the eigenvalues of these two domains? So can we get some relation between the eigenvalues? So indeed, one can get it. Okay. So for that, we also define a polarization of a function. Okay. So you look at the u and u sigma h of x. On x side, we take the maximum of these two quantity, and complement side, we take the minimum of u and u sigma h of x. Okay. So we pull the maximum of function on x side and the minimum on the h complement. Okay. So now this is that you can do on Rn, okay. And if it is on omega, you extend this function, just do the zero extension on Rn, and then look at the pH of u theta and restrict it on pH of omega, which will give you a function on pH of omega. Okay. And one can verify many properties of this pH. This is just a set theoretic calculations. Okay. So the important one is like if omega is not equal to pH of omega or not equal to sigma h of omega, okay. So then we will have a certain set AH of omega and BH of omega. So basically this, which will have a non-empty integer. So this is something important. All the things are some one can verify using the definition. Okay. And another important property is that, okay, so this pH of U preserves this gradient. Okay. So the polarization preserves the LP norm of the gradient. Okay. So whereas in the case of symmetrization, short symmetrization, it decreases the gradient norms, LP norm of gradient. So here it preserves both the gradient and LP norms of U. They are all preserved under polarization. And then it's a very easy consequence what we did in what we did in the case of short symmetrization. One can easily show that lambda 1 of pH of omega is less than or equal to lambda 1 of omega. Okay, so that just follows from this. Okay. So now the question is, can they be equal? Okay. So what one can show that so for this particular p bigger than this, okay, and if they are equal, lambda 1 of pH of omega equal to lambda 1 of omega, then either pH of omega must be equal to omega or pH of omega must be equal to CH of sigma h of omega. Okay, so we could prove that. So in other words, for this quantity, if you have a domain whose the polarization is not equal to omega or polarization is not equal to reflection of omega, then this strict inequality holds. So the idea is like, so if you look at the U tilde, which is extension of U, or zero extension of U, then pH of U is this function on this the pH of omega. Okay. So the pH of U tilde. So what we have here is so here this eigenfunction is positive, and so here this U tilde is 0 because it's a zero extension. So now if you look at the definition of pH of U, which is looking at the maximum of U tilde and U tilde of sigma h of m, sigma h of x. Okay. So since it's 0, so we get pH of U tilde must be equal to U tilde. Okay. And on this side, we will get pH of U tilde is strictly bigger than U tilde. Okay. And then so we can find a board. So basically, you can look at the boundary of this set. Okay. And if you look at on the boundary, so what we get is on a board, we get points where both the points will be, okay, like where pH of U tilde equal to U tilde and pH of U tilde bigger than U tilde. Okay. So let's look at these two sets where pH of U is strictly bigger than, and here is pH of U equal to U. Okay. So now what happens on B? Okay. So if lambda 1 of pH of omega equal to lambda 1 of omega, on this set, both this pHu and U satisfy this equation. Okay, both this satisfies this equation on B. Okay. Then we have strong comparison principle which works for P bigger than this, okay, which tells that this is equal to 0 and U and V are solutions of this equation where U is less than or equal to V. Okay, and it satisfies this equation in a distribution sense. Then U must be strictly less than V, or it must be U must be equal to V. Okay, so this is a strong comparison principle which works for this particular. Okay. Now, what we know about this U and pH of U both satisfy this equation, and we always have pH of U is bigger than or equal to U. Okay, but on this set B, we have points from both MU and NU where it's like we have strict inequality, pH of U is strictly bigger than U, and we also have points where pH of U equal to U. Okay, and that basically a contradiction. Okay, so that contradiction arises that we are assuming this lambda 1 of pH of omega equal to lambda 1 of omega. Okay. So therefore, if we have any domain where this pH of omega is not equal to omega or pH of omega not equal to sigma h of omega, we have a strict inequality. And how does it give monotonicity result? Okay. So that is very easy. So for example, this domain, like a domain with a hole. Okay. So if I take S1 and S2, these are two centers of this eccentric angular region. Then if I take at this this hyperplane passing through S1 plus S2 by 2, okay, so one can easily see that the pH of omega S1 is omega S2. Okay, and these two domains are different. Okay, so therefore, by the previous result, we must have the lambda 1 of this one must be strictly less than lambda 1 of lambda 1 of S2 must be strictly less than lambda 1 of S1. Okay, that's the previous result. And this does not require this holes to be of a ball. Okay, so the result what we proved with Vladimir, we need the balls. The inner one is ball and ball. Okay, so here we can have any shape. Okay, so as long as this perturbation stays inside, okay, we can do this business. Okay, but it works only for this particular P. But if we can generate this maximum principle for other P's, we can get even for other domains. And we use this same techniques even to get some rotation of like a ball inside or many other any other variations. We could prove the monotonicity just using the fact that if pH of omega not equal to omega, we get a strict inequality in the product. Yeah, these are the other open problems. So we could do it with the outer Neumann and inner Dirichlet. So this problem is not known when you have inner Neumann. So we did some numerical computation which shows that at certain point it decreases, then it increases. We don't know. Analytically, we don't have any way to do it. Then for this Dirichlet, if you have two Dirichlet, this extreme domains for two Dirichlet with in high dimension is completely. Yeah, I'll stop here. Thank you.
Any question?
And what about second eigenvalue?
Yes,
For
second,
example,
yeah,
monotonicity property.
monotonicity is known, I think, in for Laplacian in certain cases. And extremums are like depending on the, I think it's the connectedness and all, we have different. Right? It's a stadium type or union of two balls will maximize. I think for the connected, you don't have any.
Yeah, for the connector there is
No maximum.
More complicated situation. Sometimes something not, in some cases something is known.
Can you also prove lower bounds? You always prove that you can maximize it.
So that for this kind of domains with holes, it was always we get the result in the maximum side.
I mean,
okay, so
in my,
yeah,
I always needed the lower bound for the first eigenvalue. Just because once you know it, then it means that you can bound L to norm by the norm of the gradient. And then you need the upper bound for the resi
all right, okay.
for
So
the eigenvalue. But to prove the lower bound, it's a much more simple issue, because you cannot use just some test function. The only two at the beginning you have is just the temporal inequality, and that's all. So can you say something like the minimum of the eigenvalue is attained by some
yes, so
configuration?
for example, this case when it touches, that's a minimum kind of thing, but we don't.
So if, for instance, exactly in such a problem,
Yeah.
but not for the both but for some arbitrary domains, can you prove that the minimum of the eigenvalue will be changed at some?
Okay, so yeah, for example, if there is no domain without hole, then it's like we know the ball elements.
Okay,
Right?
but for instance, you put a hole of some fixed
Right.
dimension.
With hole, yeah, I didn't see any result.
Maybe as here, so it just depends on the boundary condition, depends on the geometry. So
yes, exactly.
Yeah.
So for instance, you have a normal hole and outer directly. And then, for instance, the question. So the one of the questions which I had to solve in some of my loops is that you have like a ball, for instance, with outer, and you put the Dirichlet condition on its boundary, and then you cut out some holes, and then you need to know some uniform lower bound for the first eigenvalue.
Okay.
For instance, you say that all the holes are inside some balls, and you impose some conditions
That's
to the
good direction to look at. Yeah, we didn't.
because once you know it, then you can bound L2 norm
Right.
by the norm of the
True.
gradient, and this is needed in many problems. For instance, in the homogenization problems.
Okay.
Quite important.
Yeah, that's a good problem to look at. We didn't.
So you don't know.
We don't. I don't. We didn't see
Basically, it was the
it.
last open question. It's exactly about that. Dirichlet outward, Neumann inside. So this, I guess, this picture, the first one, was a very particular case of your question. It's just like open questions. Hard.
Yeah. So here also we are looking for the bound from above, but this question is like, can we find something from lower also? Yeah.
More questions?
Do we have some applications about this control of the solid state with holes?
We didn't
cracks,
look at
no?
any application like general sense,
Some
but
ultrasound
yeah.
control of the solid state. No?
But we looked at some application like that we are interested, like something about radial, non-radiality of second eigenfunction.
It's applications inside mathematics.
Inside mathematics,
Inside
not
mathematics.
That's okay.